How do actuators work in feedback control systems? Imagine a robot are moving smoothly to pick up an object. How does it know exactly where to go and how hard to move? That's where actuators come into play. They are the muscles of control systems, turning electrical signals into physical motion or force. When a control system wants to adjust something, it sends a command to the actuator. The actuator then moves or applies force based on that command. In electrical engineering, actuators are often electric motors, solenoids, or linear actuators. Electric motors like direct current motors and stepper motors are common because they can precisely control position and speed. Solenoids are simple devices that push or pull when energized, often used for small movements. Linear actuators extend or retract in straight lines, perfect for applications like robotic arms or adjustable beds. The control system also uses sensors to measure what's happening in the system. These sensors could be Hall effect sensors, which detect magnetic fields, or potentiometers that change resistance as they move. Limit switches are also used to tell the system when a part has reached its endpoint. The sensor data is sent back to the controller, which compares it to the desired target or set point. The controller then calculates the difference or error between the actual output and the target. It sends a new electrical signal to the actuator to correct that error. For example, if a robotic arm is not in the right position, the controller adjusts the motor's power until the arm reaches the correct spot. This process happens very quickly, constantly updating to keep the system stable and accurate. Positional feedback devices are key to this process. Hall effect sensors detect magnetic fields from the motor's shaft, giving real-time position data. Potentiometers change resistance as the actuator moves, providing a voltage signal that indicates position. Limit switches tell the system when the actuator has reached its maximum or minimum position, preventing damage. This feedback loop makes the system more reliable and precise. Without it, actuators would operate blindly, risking errors from external forces or load changes. With feedback, the system can adapt to disturbances and maintain the desired output. For example, in a robotic arm, the actuator can compensate if the load shifts or if there's resistance, ensuring smooth and accurate movement. In essence, actuators are the physical link that carries out the commands from the control system. They turn electrical signals into motion or force, while sensors provide the real-time information needed to keep everything on track. This interaction forms the foundation of many modern automation and control applications, from robotics to manufacturing processes.